As a final set of properties in lecture 2, let us consider the mechanical behavior of thermoplastics. On a comparative basis, the modulus of elasticity is typically low for polymers by 2 to 3 orders of magnitude compared to metals and ceramics. The tensile strength is lower, it's typically about 10% of a metal. It has a much lower hardness in metals or ceramics, and the ductility, on the other hand, is much greater. It can be more than 500% for polypropylene, which is more than a couple of orders of magnitude for many metals and ceramics. Here's a typical stress strain curve for a number of different polymers at different temperatures. So for a glassy polymer or a semicrystalline polymer below Tg, it behaves more closely to a brittle material. If you change the molecular structure, the molecular weight, the nature of cross-linking, or the temperature, here is what is the case for an elastomer. It ends up being a case where you end up having a very high elongation before failure. And for a semicrystalline polymer that is above the glass transition temperature but below the melting point, you go through a yield point before you finally have failure. So the area under the stress strain curve can be pretty high. You get a very tough material under those conditions. So these are some basic differences between a typical elastic solid behavior, Hookean behavior, if you will, that you will see for metals and ceramics. When you begin to add fillers and create composites, this is a case of how the ratio of the filled material modulus to the unfilled material varies as a function of filler concentration. And typically, the Guth equation which you have seen for the case of viscosity also tends to be useful in this case, with the coefficients being a little bit different for higher particular contents. It says that for a variety of particles, this behavior describes the mechanical properties. Like the overall modulus increases as you add fillers, it becomes a stiffer material. Because the particle itself is isotropic, the directionality of the modulus is also isotropic. When you begin to add fibers to create composites, for instance, glass filled nylon, you end up getting anisotropic properties. The properties in the longitudinal direction is different from the direct properties in the transverse direction. The Halpern-Tsai equation is very useful for describing how the longitudinal modulus and the transverse modulus change in the matrix as a function of the volume fraction of the filler. In addition, you have some other constants that begin to take into account the L over D ratio or fiber aspect ratio, so the shape of the particle that is being used in the composite. So in the direction of the fiber, that's where the longitudinal modulus is defined in this manner and tends to be higher than in the transverse direction where there's lower load bearing capacity across the diameter of the fiber. And Halpern-Tsai also derived what that might look like in the transverse direction. And you can see for a given volume fraction, say 0.5, in the longitudinal direction it's over 4,000, and in the transverse direction it is lower than 1,000. That is the kind of anisotropy. Again, it depends not only on the matrix modulus, but also the volume fraction of the fiber and the shape of the fiber. So to recap, thermoplastics show a combination of elastic behavior, as we saw earlier, and viscous behavior for fluids that we saw when we looked at rheology. So viscoelasticity defines behavior of many of the polymers and polymer melts. It can be seen, for instance, in the case of a polymer being extruded during fuse deposition modeling. As it's pushed through the nozzle, compared to the diameter of the nozzle, you end up having a spring back effect, and the diameter of the material that comes out is a little bit higher than that of the diameter of the nozzle itself. Here are some examples of properties of thermoplastics used in additive manufacturing. This is a nylon 12 that is fabricated by one of the processes as a powder called selective laser sintering. You will see that you can get, for instance, a tensile modulus or a tensile strength of about like slightly under 50 megapascals. If the same material is processed by another 3D printing method called fuse deposition modeling, where it is processed as a filament, you can see that the tensile strength is a little bit lower. It is closer to 50 in one direction, but below 40 in another direction. Depending upon the print conditions in this case and the printing method, when you compare SLS and FDM, you can have different levels of anisotropy in properties for the same material or similar material. Here's a copolymer acrylonitrile butadiene styrene ABS copolymer processed by fused deposition modeling. It has a tensile strength below 40 megapascals as well, slightly lower than that for a nylon, but its impact strength is much better. Here are some websites that give you more information from Stratasys about some of these properties. In contrast, PEEK was one of the materials that we saw in the first part of lecture 1. Its strength is more than twice what you typically see with some of the other polymers such as nylon, 90 megapascals. This is from EOS as one of the sources of this material. It was processed in a particulate form by selective laser sintering. To summarize, we looked at flow properties, densities, and melting properties of polymers, the thermal properties, which are lower than those in terms of conductivity for polymers relative to metals. Heat capacity is much higher. Mechanical properties was another attribute that we looked at, much lower than what you might see in terms of strength and hardness for polymers compared to metals or ceramics, but much higher ductilities. We saw that we can alter the polymer structure or the nature of the filler or the amount of filler to affect these properties, not only in the final product, but also to take into account different effects on process conditions, printability, if you will. The design equations that we covered allowed us to be able to design materials with specific properties for specific endpoints with specific predictable processing characteristics. So that's the holy grail. Not to just develop new materials, but know whether it will be useful beforehand and know whether it can be created into dimensionally precise shapes beforehand, rather than going through a whole lot of experimentation, which is expensive and time consuming. So the design rules for materials, for filled polymers, was introduced because they come in very handy to be able to design for function and processability by changing material composition. We also rounded it up by looking at examples of thermoplastics, especially those used in additive manufacturing. In the next class, we will look at some 3D printing processes specific to thermoplastics. Here is an artificial heart section that is printed at St. Thomas Hospital to understand surgical procedures before operating on an infant.